Hello everyone. Let's begin today's concept with something you experience daily, braking your bicycle or hitting the accelerator in a car. Ever thought about what really changes when you do that? Well, that's acceleration, the heartbeat of changing motion. Acceleration is defined as the rate of change of velocity with respect to time. The formula goes A equals delta v divided by delta t, where delta v is the change in velocity and delta t is the time taken for that change. It was Galileo who observed that velocity doesn't change with distance but with time. Through experiments on inclined planes, he showed that free-falling objects accelerate uniformly over time. Acceleration is a vector quantity, meaning it has both size and direction. If your velocity increases in the same direction as motion, acceleration is positive. But if velocity decreases or reverses, acceleration becomes negative. As we go deeper, we'll learn how acceleration drives motion in every machine, projectile, or planet in motion. Let's now understand the two types of acceleration, average and instantaneous. Average acceleration is defined over a time interval. It is calculated as an average equals open bracket v to minus v1 close bracket divided by open bracket t to minus t1 close bracket. This gives you the overall rate at which velocity changed during that time. But what if we want to know how quickly the velocity is changing at a specific moment? That's instantaneous acceleration, found using calculus. The formula is A equals dv by dt, which means the derivative of velocity with respect to time. Graphically, the instantaneous acceleration is represented by the slope of the velocity time curve at a particular point. The steeper the slope, the greater the acceleration. So, just like velocity gives a snapshot of motion, instantaneous acceleration gives a precise pulse of how motion is changing right now. Here's a key idea. Acceleration isn't always about speeding up. Acceleration depends not just on magnitude, but also direction. That's why we care about its sign. If an object's velocity and acceleration are in the same direction, the object speeds up. But if they are in opposite directions, the object slows down. Let me give you an example. A car moving forward while slowing down has negative acceleration if we've chosen the forward direction as positive. And in vertical motion, we often choose upward as positive, which means gravity, acting downwards, gets a negative acceleration. These signs aren't just mathematical symbols. They help us make sense of motion in real space and time. Let's bring graphs into the picture. They're your best visual friend in physics. On a velocity-time graph, the slope of the line gives us acceleration. The formula is A equals delta v divided by delta t. A straight sloping line means constant acceleration. A horizontal line means zero acceleration. Velocity isn't changing. Now here's something really cool. The area under the velocity time curve gives us displacement. Yes, area under a curve becomes motion on the road. Then we have the acceleration time graph. If the graph is a flat line above the time axis, acceleration is constant and positive. If it dips below, it's constant but negative. Take a look at figures in the textbook. They beautifully show motion with increasing, decreasing, and reversing acceleration. Voiceover script. Let's zoom into real-life examples where acceleration plays a starring role. Free fall is a textbook case of uniform acceleration. Near Earth's surface, an object accelerates downward with g equals 9.8 meters per second squared. When you apply brakes in a car, you're actually producing negative acceleration or deceleration to reduce speed smoothly. In roller coasters and elevators, acceleration defines how intense or smooth the motion feels. A sudden change makes your stomach drop. That's physics in action. And back in Galileo's lab, inclined plane experiments showed that acceleration under gravity was constant, a breakthrough that shaped modern kinematics. So, whether it's satellites or seat belts, acceleration controls how quickly and safely we change velocity. Time for a worked out example. Let's compare average and instantaneous acceleration. Suppose an object's velocity increases from 10 meters per second to 20 meters per second in 5 seconds. Let's find average acceleration. Step 1. Use the formula average equals open bracket 20 minus 10 close bracket divided by 5, which gives average equals 10 divided by 5 is equal to 2 meters per second squared. Now, let's say the velocity is given by the function v equals 3t squared. To find instantaneous acceleration at t equals 2 seconds, we differentiate dv by dt equals 6t and plugging in t equals 2, we get 6 into 2 is equal to 12 meters per second squared. So here, the average acceleration over 5 seconds is 2, but the instantaneous acceleration at t equals 2 seconds is 12, clearly showing how acceleration can change over time. As you can see in the velocity time graph, the curve gets steeper, indicating increasing acceleration. Let's quickly recap what we've learned about acceleration, the engine behind changing motion. Acceleration is the rate of change of velocity. It can increase speed, reduce it, or even reverse motion. We learned the difference between average acceleration and instantaneous acceleration and how to calculate both. Using graphs, we explored how slopes give us acceleration and areas give us displacement, making graphs a powerful tool in physics. From falling apples to rockets taking off, acceleration is everywhere, shaping how objects move, collide, and travel through space. I hope you now have a better sense of how acceleration drives motion in machines, in nature, and in space. In the next session, we'll explore how constant acceleration leads to powerful equations of motion, your first true toolkit for solving real physics problems. Until then, keep observing motion around you. It's all physics in action. See you soon.